Hi, today in this video I'm going to explain how to calculate the total resistance of resistors when they are connected in series and in parallel, and how to calculate the total capacitance of capacitors when they are connected in series and in parallel. First of all, what on earth is a resistor? A resistor is a device which limits the current across a component. These can be useful for limiting the current across an LED to not let it burn. In real life, this is how you'd normally find small resistors in circuit boards. These rings are the color code for the resistance. There are color coders online which from the rings can calculate the resistance of your resistor. What on earth is a capacitor? A capacitor is a device which stores electrical energy. Capacitors can come in many sizes, and there are many types of capacitor. Here is a 2.2 millifarad 35 volt capacitor from my power supply. I will be explaining how capacitors and resistors work in another video. I have two resistors connected to my battery, connected in series. One has a resistance of 5.1 kilo ohms and another of 100 ohms. Now how on earth do I calculate the total resistance? Well, this formula is how you calculate it. RT, which is the total resistance, equals R1 plus R2, which are the resistances. R1 has a resistance of 100 ohms. R2 has a resistance of 5.1 kilo ohms. Now, this equation says you have to add those together. So 5100 plus 100 is 5200. So now you know that the total resistance of these two in series is 5.2 kilo ohms or 5200 ohms. In real life, you have differences because the resistance is not exact. There are wire resistances, resistance of this wire, and there are some imperfections. But you probably get the idea now. The higher the resistance in a circuit, the lower the current. This LED is connected directly to the 100 ohm resistor. It is glowing quite brightly. What happens when I connect it to the 5.1 kilo ohm resistor? As you can see, it is much dimmer now. Because the resistance is much higher and so the current is much lower. If the voltage is constant, that is. Now I have my two resistors connected in parallel, as you can see. Now what is the total resistance of these two connected in parallel? Is it still 5.2 kilo ohms? Of course not. This is the formula we use to calculate resistances in parallel. 1 all over resistance total equals 1 all over resistor 1 plus 1 all over resistance value resistor 2. This is how you work it out. So, resistor 1 has a resistance of, in this case, 100 ohms. So it ends up as 1 all over 100 ohms. Plus 1 all over the second resistor, which has a resistance of 5.1 kilo ohms. So we do 5100 ohms. Now we get how to find the common denominator between these two, which in this case is 5100. 100 times 51 is 5100. So we multiply the numerator, which is 1, times 51, and so we get 51. 51 plus 1 is 52. Hence, we will get 52 all over 5100. Now we swap the values around. So now instead of 52 all over 5100, we get 5100 over 52. And now we simply divide 5100 by 52, which will get us about 98.1. And that is the total resistance of two resistors. One the resistance of 100 ohms and another of 5.1 kilo ohms, with those two connected in parallel. I'm going to show this in practical of how the resistance decreases dramatically when I connect a 100 ohm resistor and parallel to a 5.1 kilo ohm resistor. I now have my circuits. This is an open circuit. I'm going to connect resistors here. I'm going to turn off the light and you should see what happens to the brightness of the bulb when I connect the resistors. As you can see, it is dark now. I'm going to connect the first resistor, one with a resistance of 5.1 kilo ohms. The bulb glows, but very dimly. Now watch what happens to the bulb when I connect the 100 ohm resistor. As you can see, it's glowing much brighter now, because the resistance dropped a lot when I connected the 100 ohm resistor, from more or less 5.1 kilo ohms to about 98 ohms. Here I have a capacitor with a capacitance of 2.2 millifarad charged with a voltage of 9 volts DC. Watch what happens when I connect it to the bulb. There are no power sources. The only power source is the capacitor in this setup. As you can see, the capacitor discharged into the bulb and the bulb glowed. Now you may think that when it comes to capacitors connected in series, I just add one capacitance to the other. Well, for capacitance it is the other way around. In series capacitance form, when we're connecting capacitors in series, to calculate the total capacitance of the capacitors, we use this formula. 1 over capacitance total equals 1 over capacitance of one capacitor plus 1 over 1 plus 1 all over 1 capacitance of another capacitor, and so on. The more capacitors we add, the more capacitances there are. Same with resistors, except with resistors, the more resistors we add, the more resistances there are. In the example I'm gonna use, I have two capacitors of the same type. Each have a capacitance of 2.2 millifarads and a voltage of 35 volts. So, to calculate the total capacitance of these two connected in series, we do this. 1 all over 2200, this is in microfarads, plus 1 all over 2200, this is in microfarads, equals 2 all over 2200. We swap the values around, so that's 2200 all over 2. And this leaves us with 1100 microfarads. But this is a microfarad. So we are left. So now we know that the capacitance of these two in series, the total capacitance is 1.1 millifarads or 1100 microfarad. I'm going to put what I just said in practical. I have charged these two with my 9-volt battery. And now I'm going to connect them in series. As you can see, the positive is going with the positive wire, positive terminal. And the negative of that with the positive of the other capacitor. Never short circuit capacitors. Life lesson number 1. And remember that YouTube viewer, never short capacitors. Capacitors can go out very high short circuit currents. Anyway, let's do this. Look at the bulb now. As you can see, it went off quickly. It glowed for a shorter time because the total capacitance was lower. Note that when I connected these capacitors to the power supply for charging, I did not connect them in series. I charged them individually and then connected them in series. But in the parallel capacitances formula, however, we just add the capacitances together. So total capacitance is the capacitance of one capacitor plus the capacitance of another capacitor. In this case, we have 2200 microfarads plus 2200 microfarads. which leaves us with 4,400 microfarads, or 4.4 millifarads. And now I'm going to prove this. Now let's connect the capacitors and let's connect the capacitors. Always connect capacitors correctly. Always connect them in the correct polarity. Otherwise it won't end well. Okay, so now I've connected the two capacitors in parallel with the correct polarity and at the same voltage. The capacitors are charged at the same voltage. And now look what happens when I connect them to the bulb. I'm going to turn off the light so you can see the bulb. You've seen it before, but this is for fun. Correct polarity, connect it to one side, connect it to the other, and light up for a very long time, as you can see. Much longer than before. And this proves that if we connect capacitors in parallel, the capacitance increases, and if we connect them in series, the capacitance decreases. Okay, so my experiments today have proven why resistors connected in series increases, and when resistors are connected in parallel, resistance decreases, and why capacitance increases when capacitors are connected in parallel, and why capacitance decreases when capacitors are connected in series. I hope you enjoyed the experiments, and I hope you enjoyed the video too. And please, don't short circuit capacitors. Very high currents will flow and it won't end well. Also, when connecting capacitors in parallel, make sure that the voltages are the same and that the polarity is correct. Otherwise,